very own Nick Dory, who with perfect intermediate technology, which I'm pleased to see hasn't disappeared, and bouquet and slides, is going to speak about singularities and magnon S matrix.
Okay, thanks very much. I'm going to give a talk where I'll hopefully get towards the end of the talk to some work that I did in March with Diego Hoffman and Juan Maldacena on the analytic structure of the magnon S matrix in the spin chain description of planar n equals 4 super Yang-Mills. It's also based on an earlier paper I wrote last year. But I think, given the mixed nature of the audience, which ranges from mathematicians to total experts in the subject, I'm going to try and mix it up and actually give an introduction and a review of the kind of whole of this area. So hopefully I'll be able to fit all of this into the allowed time, but if not, something we'll have to give. Okay, so what's the basic problem? The basic problem is the statement of the ADS-CFT correspondence. I'm already getting a problem here. The fan is... The basic statement of the ADS-CFT correspondence is an equivalence between the observables, a matching between the observables of two very different theories. It tells us, conjectures, that the spectrum of operator dimensions in n equals 4 super Yang-Mills in the large n limit, in other words the planar limit, should be the same as the spectrum of free strings on ADS5 cross S5. So after 10 years of this conjecture, it's certainly not the case that we're in the position to prove or yet even demonstrate the validity of this conjecture for generic observables like generic operators rather than BPS operators. And as most of you I'm sure are aware, the main problem in actually verifying this or attempting to, well, verifying this statement about the equivalence of the two theories and their spectra is the fact that effectively the two theories are weakly coupled in very different limits. So in particular, even though we've taken the large n planar limit, n equals 4 super Yang-Mills still has a Toft coupling. So that's the combination g squared n, which is held fixed as n goes to infinity. And that coupling controls the loop expansion, in other words, the expansion in planar diagrams of n equals 4 super Yang-Mills. So when lambda is much less than 1, the super Yang-Mills side of the correspondence is weakly coupled, and we can calculate the first few orders by evaluating planar Feynman diagrams. However, on the other side of the correspondence, lambda also enters, and it enters in a different way. It's this effective size of the ADS5 cross S5 geometry in units of the string length scale. Now, even though the way I've formulated the correspondence, I'm talking about free strings, strings with no interactions between pairs of strings, for example, there is still the problem of working out the spectrum of a single string. And that problem corresponds effectively to solving the worldsheet string sigma model, the two-dimensional quantum field theory that describes the propagation of the string in this geometry. And that itself is an interacting nonlinear sigma model, effectively. And generically, this is only weakly coupled when the geometry is much, much larger than the string scale, and we can neglect sigma model loops which correspond to alpha prime corrections. So in general, for sort of generic observables, the problem is very hard. To go beyond these two regimes, we'd either have to try and solve the string sigma model directly as a two-dimensional quantum field theory, or we'd have to find a way of attacking the old problem of directly summing up the planar diagrams in non-abelian gauge theory, which of course is something that's very, very hard. So the reason that there's been a lot of progress and things are not as bleak as they were 3 or 4 years ago is because essentially of the discovery of integrability on both sides of the correspondence. I'll be a little bit more precise about what I mean by integrability as the talk goes on, but for the moment I'll just define integrability as the occurrence of a huge number of unexpected conserved quantities. In addition to the familiar conserved quantities like energy and global charges, integrable systems are characterized by the fact that they have as many conserved charges as they have degrees of freedom. And this typically is something that you can exploit to find the spectrum of such systems exactly without relying on any perturbative analysis. So integrability is shown up independently on both sides of the correspondence. In particular, this line of development was started by Minahan and Zarembo, who observed just at one loop on the gauge theory side that the complicated problem of diagonalizing the dilatation operator, in other words, finding the full spectrum of anomalous dimensions, could be mapped onto an integrable problem, specifically the problem of diagonalizing an integrable spin chain, finding its exact energy levels. And I'll review the spin chain picture coming up shortly. So that might have been an accident, but in fact, it persisted. It's persisted in all perturbative checks. It goes beyond one loop, certainly. Complete checks of this property of integrability have been made at one loop, and partial checks have been made at several higher loops. And in fact, the consequences of integrability have now been tested up to 4 and 5 loops. But even so, one might have worried that it's an artifact of gauge theory perturbation theory in some sense, and not a feature of the full problem. So it's very, very encouraging, and it was another important strand to this development, that exactly the same kind of structures a little while later were isolated on the string side of the correspondence. So here we're initially talking about the limit where the string theory is directly tractable, which is the limit of very, very large Toft coupling, where you can basically think about the strings, or at least large string solutions, large string motions, as being described by classical solutions of this worldsheet sigma model. And it was discovered by Benner, Polchinski, and Royban that this string sigma model, this two-dimensional quantum field theory, its classical equations of motion, are in fact integrable in exactly the same sense that I described. In other words, that you can construct, in fact, an infinite tower of hidden conserved quantities. And in the classical theory, that actually allows you to find the generic solution to the classical equations of motion, even though that equation of motion is highly nonlinear. So roughly speaking, alpha prime corrections will be, a major subject of this talk, effectively. So that will be addressed as I proceed. If it's not addressed, then ask me again. So basically, the encouraging picture is that one finds these structures appearing on both sides of the correspondence. At small lambda and at large lambda, although of course we're interested in actually resumming all orders in lambda expansions and finding exact results, even in the first orders, solving for generic observables on either side is a hard problem, but it turns out to be an integrable problem. And in fact, analogous structures, as I said, arise on both sides of the correspondence. So in particular, on both sides of the correspondence, we uncover a one spatial dimensional system, or 1 + 1 dimensional system, if you like, which is integrable and is subject to periodic boundary conditions. And I'll review why that's the case as we go on. But basically, that system is the spin chain that I mentioned on the previous transparency in the context of gauge theory, and it is nothing other than the closed string, the free closed string on the string theory side. Now, the hope is, as that integrability has been discovered at small and large lambda, it will be a feature of the problem that persists for all values of the coupling constant. And in particular, that's equivalent to demanding that the sigma model is quantum integrable on the string side. Now, if that's the case, we expect generically that we will be able to exploit integrability by a standard set of techniques to find the exact spectrum of the problem and really solve this problem and find the generic observables in the spectrum and their interpolation as a function of the Toft coupling. And that's by a set of methods which I will talk about a little bit later, called the beta ansatz, which exploit the existence of these high conserved charges and reduce the problem of finding the spectrum to a set of algebraic equations. That is still an unsolved problem of finding the exact set of beta ansatz equations which interpolate between the two sides of the correspondence. However, although that problem, which is of course the problem we really want to solve, has been, there is still some severe obstacles to solving that, which we'll talk about what they are. There has been a huge amount of progress in the last 2 years in a particular, by taking a further limit of the problem, which leads to dramatic simplifications. And that limit can be described very simply on both sides. It's a limit in which one of the global charges of n equals 4, one of the r charges, goes to infinity, and the effect on both the spin chain and the string is the same. It takes the one spatial dimension with periodic boundary conditions and basically replaces it by a spatial dimension on an infinite line. And the problem then becomes one of finding the spectrum of this system not subject to periodic boundary conditions, but rather subject to boundary conditions which we're much more familiar with in quantum field theory, essentially vacuum boundary conditions, that the energy density goes to 0 as you go to either left or right infinity. So in that limit, you'd expect in general quantum systems, integrable or not, we have a generic expectation, provided that they have a mass gap, which in fact is the case here, that you can think about the system in terms of a set of asymptotic states, and you can describe the transitions between those states by an S matrix. So basically, the aim, once you take this limit, for understanding the full spectrum of the problem, is to find the spectrum of asymptotic states and to find the exact S matrix which describes their scattering. Without integrability, that would be a very formidable task. But in the presence of integrability, there is a generic consequence of the existence of these higher conserved charges, which makes the problem tractable. And that is the property of completely factorized scattering, which I will talk about as we proceed. Well, basically, it comes because we're expanding around the string ground state in this limit of large J. So it's an expansion around a particular background for the string. And if you look at the string oscillators around that background, sometimes called the plane wave limit, you discover that they actually have mass terms. So the worldsheet theory in this limit, expanding around this particular background, is massive. And there's no contradictions with the usual kind of conformal field theory picture of strings, because here we're working in a completely gauge-fixed formalism. So it's Green-Schwarz in completely gauge-fixed formalism. So, to continue this overlong introduction, basically, to bring the story right up to date, that problem, we now believe, has been solved completely, basically by a series of developments led by Beisert and Staudacher. There are now very compelling conjectures, both for the spectrum of asymptotic states and the spin chain, both the elementary excitations and also a rich spectrum of bound states on the infinite spin chain or the infinite string. And we believe we have a complete description of that. And also, more importantly, a complete description also of their scattering in terms of an exact S matrix for the system. Again, this development was led by Beisert, culminating in a conjecture for what the exact two-body S matrix is due to Beisert, Eden, and Staudacher. The structure of these conjectures, particularly for the S matrix, contains a large degree of mystery. They're very mysterious, and the ingredients which go into them are still somewhat mysterious. But I will try, in the latter part of the talk, to partially demystify them. Also, I should say they're still conjectural, but they've now been subjected to remarkably precise tests, both in the limit of small and large lambda. So the main thing I'm going to emphasize, and the main theme of our work, once we know what this spectrum is that if you have an exact description of the spectrum, then you have some very, very precise constraints on the S matrix through a very old-fashioned connection, which is familiar in relativistic theories, that the singularities of the S matrix can be related to and identified with processes in which there occur in the scattering on-shell intermediate states. The simplest example being a pole when you form a bound state. And in fact, this leads to a very precise set of constraints on the S matrix that are satisfied by the BES conjecture, although they were certainly not ingredients which were put into the BES conjecture. So a highly non-trivial test. And I should say that although I'm talking in the language of this infinite chain, the spectrum and the S matrix, these are precisely the ingredients that you want to go back to the periodic problem. As long as the chain is very, very long, you can take the spectrum and the S matrix, subject it to periodic boundary conditions, and come up with a set of all-loop asymptotic beta-ansatz equations. They're all loop because they contain all orders in the 't Hooft coupling, but they're asymptotic because they only, in this case, apply for a very, very long chain where this picture of the spectrum and the S matrix is essentially valid. And there are exponentially small corrections in the length of the chain. But the achievement, the concrete achievement which this development gives you, is now basically the exact anomalous dimensions for generic observables. The only constraint, generic observables in the planar theory, in other words, generic operators, the only constraint being that those operators are suitably long so that the asymptotic spin chain picture works. So all operators which are long enough, up to exponentially small corrections, we now believe that we know their exact anomalous dimensions, or we can reduce it to a set of algebraic equations. So I'm going to start with a warm-up, which will be very, very tedious for the experts in the audience, but hopefully will be enough to for those who are less expert to get some sense of what's going on in the subject and how this works. And then I'll move on to, and I should say also that if you were here a couple of weeks ago, this first section will have some overlap with Kostya-Zarembo's lectures and also with Nicholas Bizet's lectures in the school that has just occurred here. And then in the second part of the talk, I'll move on to discussing what we've learnt about the exact asymptotic spectrum and the S matrix. And I hope I get there in time to talk about the S matrix and its singularities. So let's start from the beginning and review the basic development which was initiated by Minahan and Zarembo concerning just the one loop problem in the gauge theory, the problem of diagonalizing the dilatation operator at one loop. In other words, finding all one loop anomalous dimensions. And in fact, what we're going to do is immediately focus just on a subsector of all of the operators, all of the local operators. And that subsector will be single trace operators which are built from two of the three complex scalar fields in the n equals 4 theory. Recall that n equals 4 super Yang-Mills contains 6 adjoint scalars, and those can be organized as three complex scalar fields. So we're talking about the anomalous dimensions of operators that can be made by taking traces of arbitrary powers of these two fields x and y. And in particular, the important thing is that the ordering of the x's and y's can be arbitrary. So there's actually a huge set of operators that are in this set. And I should also emphasize, in contrast to what we were learning about in Alberto and Ami's talk earlier in the week, these operators are not in general members of the chiral ring. The vast majority of them are not supersymmetry preserving operators, and therefore their dimensions are not protected. They receive quantum corrections, and in particular our aim is to calculate those quantum corrections to all orders. Essentially, it's only with certain very special symmetrizations that such an operator belongs to the chiral ring and is BPS saturated. So basically the first observation, so let me start by just defining two charges J1 and J2 which count the numbers of fields x and y that we've inserted in the trace. So the basic observation, which is essentially content-free to start with, is that obviously we can represent this set of operators by convenient notation, which is to think of them as a chain of spins where spin up is identified with x and spin down is identified with y. The trace that we're putting in and the cyclicity of the trace means that actually we have to identify those configurations under cyclic permutations. So really we should think about not the full configuration space, but mod out by translational invariance. And in this language of spin chains, I can translate from the charges J1 and J2 to define, first of all, the total length of the chain, which I'll call L. And secondly, which will be an important quantum number, the number of flipped spins, the number of down spins, which is just J2. Yes?
Another difference with the previous talk is that n theory, they had finite n.
So, sorry?
They were, in principle, considering finite n.
Absolutely, right. But we now know that integrability is not expected to work at finite n. So I'm focusing primarily on the, I'm focusing only on the planar contributions. And I should mention the fact that planarity, because I'm only looking at the limit of infinite n, if you like, The planarity means that there's no restriction in looking at single trace operators only, and just a feature of large N counting that the dimensions of multi-trace operators factorized, they just become the sum of the dimensions of the single trace operators from which they're made up. Well, that's a good question, and I think there are people in the audience who know the answer to that more precisely than I do. I think you can look for the tests of integrability are basically that you can parameterize things in terms of a beta ansatz. So there are particular relations between 3 excitation states and 1 and 2 excitation states implied by that. Now, as far as I know, there are specific tests which have shown that it does fail at finite n, but not at one loop. Where I think it's true for all n at one loop, as far as I remember. It's only at higher loops that the importance of large n becomes apparent.
There are degeneracies between dimensions which follow from it.
Oh yeah, there's one very characteristic signal is a set of degeneracies to do with a kind of parity, which is implied by integrability.
You can show that degeneracy.
That breaks down. Sorry?
You can show that
2 or 3 loops it breaks down. I think it Biser's, Staudacher, and Christiansen.
Mm-hmm. So it doesn't appear to be a feature of the finite n theory, but it is believed to be an exact feature of the large n planar limit. So I'm looking at the planar contributions to the dimensions of these operators.
But what about the argument of Polchinski and Neumann?
This is classical.
That's a classical argument.
So 1 over n is G string.
So it's also large n.
Sorry?
So
Yeah,
it's
this is
also
large n.
It refers to classical string theory. If you wanted to consider quantum corrections, you would have to think about that sigma model on a Riemann surface of higher genus, and no one has directly thought about that. So it remains possible that there is integrability for the interacting string theory, but it's already, our general aim in ADS-CFT is to, for example, when we're looking at gauge theories, is to solve the planar limit. So that's the primary focus here. So, okay, let's move on to the problem at hand, which is trying to calculate the spectrum of anomalous dimensions, or in other words, trying to diagonalize the dilatation operator of the theory at one loop. So basically what Minahan and Zarembo did was to find a convenient form for the one-loop dilatation operator expressed as an operator acting on this basis of spins. So first I should say that the dilatation operator is trivial at the classical level, because for all of the single trace objects that I constructed, the dimension is just the number of scalar fields in the trace, just from classical dimensional analysis. So the interesting stuff starts at one loop, where you calculate Feynman diagrams which tell you how the dimensions differ, how the action of the dilatation operator, of scalings on this set of operators, differs once we introduce a one-loop correction. So just a piece of notation here, I'm going to expand the eigenvalues in terms of the anomalous dimension is the eigenvalue of the dilatation operator, the length of the spin chain is just the classical contribution, and the eigenvalues of this operator H, which I'll start to call the Hamiltonian, are I'll describe as the energies of the spin chain, and as a factor of lambda over 8 pi squared here. So the key discovery, based on earlier observations about pure gauge theories, non-supersymmetric gauge theories by Lipitov, is that this dilatation operator at one loop, when acting on the basis of spins, turns out to be a very, very specific Hamiltonian for that spin chain. It's a Hamiltonian which you can write in the following way. It includes 2 terms, one which just acts as the identity on neighboring spin sites, and the other which permutes the neighboring spin sites. And this is a very special operator. In particular, things like the fact that this coefficient is precisely 1 are important. Because precisely for this Hamiltonian, the spin chain is integrable. In other words, it's already been demonstrated a long time ago that this Hamiltonian is actually part of a tower of higher Hamiltonians, all of which commute with each other, therefore giving the spin chain a higher set of conserved charges, which renders it integrable. And in fact, there is a purely algebraic technique, just in terms of manipulating these operators and their representations, called the algebraic beta ansatz, which allows you to derive directly the spectrum of this Hamiltonian. And that was done a long time ago by Fadiev and Takhtajan. But I'm going to discuss integrability from a slightly different perspective, which is really relevant when we're looking at a very long spin chain. So let me just describe what the spectrum looks like, order by order, in the number of excitations or flipped spins. So as I mentioned, I'm calling the length of the spin chain L, and the number of magnons, I won't introduce that word yet, the number of flipped spins, M, I'm going to hold fixed and consider different values. So M is a good quantum number. The corresponding total spin operator commutes with the Hamiltonian. So we can organize the spectrum in terms of different values of M. So first of all, we start with 0 flipped spins. In other words, the ferromagnetic ground state of the spin chain. It's not hard to check that the Hamiltonian vanishes on that state. So the corresponding operator does not receive a non-normalist dimension at one loop. In fact, that agrees with plenty of stuff we know, because when you have all x's inside the trace, then that's one of the chiral primary operators that Amy and Alberto were telling us about. And we know that in that case, its anomalous dimension is forced to be 0 by the fact that it belongs to the chiral ring. So it's quite right that we should find 0 for the one-loop anomalous dimension when we evaluate that in perturbation theory. So something more interesting now, let's move on to a single flipped spin. We can introduce a basis for such states by just calling the state L being the state with this flipped spin on the L site. And that's, if you like, analogous to a position eigenstate for the system. But that's not a good quantum number. The position operator doesn't commute with the Hamiltonian. But because the system has a translational invariance, there is a momentum operator which indeed commutes with the Hamiltonian. So the way to construct eigenstates is to construct eigenstates of the momentum operator. So as usual, we just take a Fourier transform with respect to the position basis, and here I'll define a wave function for the states that I want to talk about. In other words, the coefficients that appear in the expansion in terms of position eigenstates. So this gives you a very nice picture of a single spin propagating with a conserved momentum along the spin chain, along the infinite spin chain. And basically you can think about the corresponding energy eigenvalue as being the dispersion relation for that excitation. So this flipped spin has a momentum, and when you evaluate the Hamiltonian on this state, you find it's an eigenstate, and its energy is related to the momentum by this characteristic trigonometric dependence. So just to remind you, the fact that you get periodic dependence on momentum is not surprising, because we have a discrete system in position space, and if you take the Fourier transform of something discrete, you end up with something periodic in the Fourier transform space. It's also known as the occurrence of a Briand zone in condensed matter systems. Okay, so that's the single magnon. That excitation, or a single flipped spin, we think of like it's a particle. It has a conserved momentum and energy, and so we call it the magnon. And that's the first, if you're not familiar with the words in the title of the talk, hopefully that's the first word in the title demystified. So now let's go on to, because the number of magnons is a good quantum number, let's go on to 2 magnon states. And here it's very straightforward, at least initially, to build up what these states should look like. The interaction Hamiltonian that I described means that the 2 spins, the 2 magnons, only interact when they're next to each other. Okay? So over the whole of the position space, the whole of the configuration space for the positions of 2 spins, the Hamiltonian is effectively free. And you can always write the eigenfunctions just as plane waves, just as we did in the case of a single magnon, basically because except when the magnons are immediately close together, the interaction vanishes, so that the same plane waves give you eigenstates of the Hamiltonian. When you try and match precisely these wave functions in the region where the spins sit together, you get a constraint which tells you what the phase difference between the incident wave and the reflected wave are. So in other words, the matching condition when the spins are close together determines what you would call the S matrix for the problem. So you think about this as the scattering of 2 magnons with an incident wave and a reflected wave, if you like. Those can differ by a phase difference, and that phase difference is what you would call in a more complicated system precisely the S matrix. So indeed, you can check that such a wave function provides an exact eigenstate, and the matching condition when the spins are close together allows you to solve for what this phase factor or S matrix is. And again, it's a kind of characteristic trigonometric function of the momenta. It involves this function phi, which is generally known as the rapidity. And the S matrix has, has a nice analytic form as a function of the momenta of the two magnons. And a characteristic feature which will be important in what follows is that it has a pole. The S matrix has a pole when the two rapidities, the cotangents of the momenta, differ by exactly one imaginary unit. So that corresponds to a case where the momenta are complex. So these scattering states make sense for all real values of the momentum. They describe possible states on the infinite chain. But in fact, you can get more from them than just that. You can also look for solutions which have complex values of the momenta corresponding to bound states. Now, what you have to ensure here when you have complex momenta is that both the exponentials here are exponentially decaying as we go to large distance, so that we get a normalizable wave function. So in fact, that can only happen for one of these exponentials at a time, and the only way to get a normalizable wave function is if you go to a point where only one of the exponentials survive. And that corresponds precisely to a pole or a zero, depending on your conventions, of the S matrix. If the S matrix has a pole, then after normalization we just keep this exponential and throw away this one. And this in fact does precisely lead you, by just analytic continuation of the momentum, to a bound state, eigenstate of the Hamiltonian for the problem. If you solve the pole condition and then just plug back in the resulting complex momenta into this plane wave, you define precisely a wave function which corresponds to a bound state. Its behavior in the two positions of the constituent magnons has a kind of center of mass phase which represents their propagation together. And then if you try and separate them by changing the difference L1 minus L2, you discover that this is a quantity that decays exponentially. So this is indeed an normalizable, an exponentially normalizable bound state of the system. And the thing that's worth noting here is that the recipe for finding such states is actually the one that's familiar from relativistic field theory. Precisely bound states correspond to poles of the S matrix. And if you find the pole, provided it satisfies certain conditions, which hopefully I'll get onto, then almost always you can find an associated bound state. And in this case, it's very explicit. It's explicit because you simply analytically continue in the momenta, and you can check that this really is an eigenstate.
Four-dimensional interpretation of these magnons physics, this scattering, because the spin chain and yeah.
Basically, I mean, at this level, what you're doing, each magnon configuration corresponds to some single trace operator, okay? And this is telling, these wave functions are telling you what linear combinations of those single trace operators are eigenstates of the dilatation operator. That's also telling you what the eigenstates of the Hamiltonian are on the theory on a three-sphere. So that then looks more like a dynamical property. They're eigenstates of the Hamiltonian of the n equals 4 theory on a three-sphere. But as yet, I don't know of any more direct interpretation in gauge theory. In string theory, we'll see that there is a more direct interpretation in terms of world-sheet solitons. But at the moment, this is just an auxiliary picture that allows you to find the eigenstates of the dilatation operator. In other words, find the exact anomalous dimensions.
But the bound state is also a linear combination, though.
Yeah, I'll illustrate that in a moment. So now, let's...
Sorry, so these are bound states when the theory is on a three-sphere. We should think of them as...
No.
They're eigenstates.
The n equals 4 theory has a set of operators on R4 which are mapped to string states by ADS5 cross S5. An alternate formulation is that the energy eigenstates on S3 are in one-to-one correspondence with the dimensions on R4.
Exactly.
Right, so you can use either of these languages for the n equals 4 theory. Every operator that I talk about has a corresponding state on S3. Yeah? So the picture applies equally.
An energy eigenstate on S3 is a bound state of particle.
Well, I don't know what a bound state means in finite volume. I mean, I don't think you can make a space-time... I don't think it fits together as a space-time interpretation in quite a simple way. Well, that's a good question. So you're basically asking, what will the state look like It's basically the state that we create by acting with this operator in radial quantization. So because we're working on a sphere, it's not clear to me, I don't think there's any sense in which it's localized at a particular point on the sphere. In fact, I know that's not the case because what we're dealing with here are scalar operators. So they're in the S wave on the 3 sphere. Yeah. Okay, so in fact, everything that I've talked about so far, I could have said in a generic spin chain with a generic Hamiltonian, and integrability has not yet played a role. In any quantum mechanical problem with local interactions, you would expect to be able to describe two particle states in terms of plane wave scattering with an S matrix. So in fact, what we now want to do is to think about the multi-magnon scattering states, and of course the same argument applies that those will also be superpositions of plane waves because for a large part of the configuration space, the magnons are just free. But in general, we could have very, very complicated multi-particle S-matrix factors which appear in that expansion in terms of plane waves. And this is where integrability enters. Because it can be shown that a generic consequence of the presence of these conserved charges is a very specific property of the S-matrix which describes the scattering of multi-particles. And that specific property is that the multi-particle S-matrix, in other words, the phase associated with the different partial waves for multi-particle scattering states, factorizes into a product of two-body factors. So that's illustrated by this diagram here for the 3-particle S-matrix. The 3-particle S-matrix can be thought of as arising from a series of 2-particle collisions. So we have, if you like, writing that out mathematically, it's the statement that the 3-body S-matrix is the product of 2-particle S-matrices. Now, what has that got to do with integrability? Well, one very simple way in which you can see the connection is just to recall the fact that if we have 2-body scattering in 2 dimensions, because we have 2 equations and 2 unknowns, the individual momenta of the 2 particles that are scattering have to be conserved. In other words, if we look at this 2-body collision here in the bottom left-hand corner, P1 and P2 go in, and P1 and P2 have to come out, just because of 2-dimensional kinematics. In general, if we were to consider 3-body scattering, we would then have 6 unknowns, and we would have more unknowns and the same number of equations in a generic problem. And in general, it would not be true that the same momenta have to come out to satisfy momentum conservation. But because we factorize the S-matrix into a product of 2-body factors, and the momentum is conserved in each constituent process, that means that in an integrable system, the set of particle momenta that emerge in the final state are the same as the particle momenta that go in the initial state. So that means that in addition to the ordinary conserved quantities like energy and momentum, you can have an arbitrary large number of additional conserved quantities. You can scatter as many particles as you like, and each individual momentum of each individual particle will be conserved. So I also want to say a word now about the bound states in this multi-particle S-matrix. You can also look for bound states of more than one magnon by looking for the appropriate poles in the 3-particle S-matrix. And generically what you need to do is to find the maximally singular point of the 3-particle S-matrix. But because we know the 2-particle S-matrix, that then just becomes an exercise in trying to implement simultaneous singularities for each of these factors. And in fact, the best you can do is to make 2 out of the 3 in this product singular by having the first and the second rapidity separated by 1 imaginary unit, which makes this singular, and having the second and the third separated by 1 imaginary unit, which makes this factor singular. So this, in fact, this pole can be used in exactly the same way to find a bound state of the 3 magnons that are participating in the scattering process. And so it goes on. In this integrable system, we can now find the full spectrum of bound states by similar methods. One can find that basically what you want to do is to find the maximal singularity of the multi-particle scattering matrix. And that basically requires that you take the maximal number of the 2-body factors to be singular. So that means that you have to separate their rapidities by 1 imaginary unit in the best way that you can, which is to make a chain of roots in the complex rapidity plane. These are known as beta strings. and they correspond directly to bound states of q magnons for each integer q. So one can evaluate the energy of these states very simply just by basically working out the energies of the constituent magnons and continuing to the appropriate complex value of the momentum, and you discover that they are genuinely bound. Not only is the magnon less in energy than the q magnons that went in, but it's actually even lighter than a single magnon by a factor of q, which is the number of constituents. So the more particles you put in, the lighter this object gets for any fixed momentum. So going back to the eigenstates of the dilatation operator, this is telling us that for a very, very long operator, asymptotically, we're going to have a set of eigenstates which look like multiple impurities bound together. So it's not going to be precisely y's at adjacent sites, but you'll have some linear combination where when you separate the y's, the corresponding terms in that linear combination will have exponentially small coefficients. So schematically, it looks like an eigenstate where the impurities that you've introduced, the y's, the y-scalar fields, like to cluster together. And this is saying that you can have such impurities for any number of constituents. You can have such bound states for any number of impurities. So this is telling us what the eigenstates of the very long operators look like at one loop. Sorry?
The energies are low, also telling us that these operators are kind of close to being protected, as it were. Close to.
I guess you could say that. I mean, it gets smaller and smaller as Q becomes larger. So there is some sense in which they become approximately. Well, there is a sense in which they are BPS, which I will describe in a minute. One thing I should have said is that physical states, because of this trace, have to include more than one excitation. You can't simply have a single excitation with non-zero momentum. Because of the cyclicity of the trace, that will just give you 0 if it has non-zero momentum. So you actually, a physical operator has to correspond to more than one excitation, 2 excitations and higher. So there actually are no states in the theory that consist of just a single excitation. They always have to have multiple excitations. So I'm thinking here of a longer chain in which we have some other impurity that cancels the momentum of the impurity that I've written down here.
So for Q equals 1,
This is just the magnon.
yeah, so you could say that the impurity is equally distributed.
Well, basically, for Q equals 1, remember we add this with a phase depending on its positions on the chain. But because the position on the chain does not matter, that sum over phases will basically give you a sum over nth roots of unity, and you'll just get 0. So the only case where you don't get 0 is if the momentum is exactly 0, in which case you're summing over the same operator L times.
Yeah, but you could interpret this phase
Mm-hmm.
as a quantum mechanical wave function.
I have. I just did on the preceding transparency.
So when you take the absolute value, you find that you take it equally at all places.
Yes, that's right. I mean, yes, I agree with that, yeah.
So when you increase Q, I guess it will become more, what you're telling us is it will become more localized.
Well, the binding energy certainly increases. So if you were to look at the wave function, it's an interesting question as to how localized it would be. Okay, it's exponentially decaying, but the exponential decay depends on the momentum. So actually the width of this bound state actually is a momentum-dependent thing. It's an interesting question about whether it becomes more precisely located, and certainly that would be your intuition, I think, that it would become more located as you had
Q is
more
bounded
and
by
more.
the total number, by total G.
Sorry?
Q is bounded by total G.
Sure, but I'm thinking in a limit where this is effectively infinite, so that bound isn't really relevant.
And is it easy to compute this distribution?
Let me think about that. Well, basically, yes, we're using Mathematica, yes. What you have to do is take the plane, you have to solve the conditions for the relationship between the constituent momenta, then plug that into a plane wave, reorganize everything in terms of the relative separations and the center of mass, and to a finite order you could do that order by order using Mathematica, but I certainly haven't done that.
If the chain is really infinite, you have this zero momentum.
Well, that's a good question. I mean, for any finite chain, if you have the trace in place, if you take the limit, then you've obviously still got the condition. But in the strict infinite limit, you need not impose that condition, right? But that's not going to be especially significant, I don't think. I mean, you simply impose this condition, you work out the spectrum without the condition, and then at the end of the story you impose that condition. But you're right, strictly speaking, when the chain is infinite, it's an optional thing, because you can have momenta flowing off to infinity. So it's actually interesting to note that in terms of the one-loop spectrum for long operators, which is the story we're going to be able to generalize to higher sectors and higher loops, this actually directly, without the need for any kind of beta ansatz, gives you a suitable basis for what the spectrum looks like asymptotically for very long operators. It's nothing other than the free multiparticle Fock space made out of these different bound states. So you just take an arbitrary collection of these bound states. Once the chain is infinitely long, there's effectively no quantization condition on the momentum, so that effectively becomes a continuum. And the different possible kind of asymptotic states, their wave functions and energy eigenvalues, are basically described by the formulae that I've written here. It's nothing other than, you know, the free set of asymptotic states for this particular problem. So in fact, this picture is useful and relevant because we're going to be able to answer very precisely the question, what happens to this picture, which, as I told you, is only valid at one loop, and only in the SU2 sector where we're dealing with the x's and y's only. What happens beyond the SU2 sector, and what happens beyond one loop, is a question that we're going to be able to address. So most of my discussion will be in the language of the S matrix and these asymptotic states, but I should just very briefly discuss the more conventional language, which is much more powerful, in fact, at one loop, because you know the Hamiltonian, which is the language of the beta ansatz. So to apply the beta ansatz, basically what we want to do now is, having found a set of states on the infinite chain, we want to take those states and place them on a finite chain. Now, because the interactions are local, and basically even if you're in finite volume, for the majority of the configuration space, the magnons propagate freely, it's essentially very straightforward to just take the problem on the infinite line and calculate the corresponding spectrum in finite volume. All you have to do is to take the M magnon scattering states that I showed you on the previous transparency. I really showed you just the 2 magnon one, but the M magnon ones are given by sums of plane waves with S matrix factors weighting each plane wave. And all you have to do is to take those states with their energies, which we know are just the sums of the energies of the constituents, and impose the periodicity condition on that wave function. And imposing periodicity, of course, tends to make the momenta discrete, so you get some set of constraint equations with isolated solutions, and those equations are nothing other than what are known as the beta ansatz equations for the problem. So just to motivate what these equations are, if we had a free system, the quantization condition on the momenta would just simply be, for each momentum, given by the equation where the right-hand side is replaced by unity. That would tell you that P is quantized in the usual units of 2 pi over the length of the chain. The difference is that now we have additional phase shifts that come from the pairwise scatterings of the particles involved. So when you take one particle and shift its position right around the chain, it doesn't just pick up its phase from free propagation, you also have to include the phases it picks up in scattering with the other particles. And because it can be described purely by a factorized S matrix, the resulting factor that appears on the right-hand side here is simply a product of the 2-body S matrix that we established before. So in fact, in this problem, once you know the dispersion relation of the elementary excitations, and you know the S matrix, then actually that's the complete solution, because it allows you to directly write down the beta ansatz equations for the system. So basically that's the key thing, is the ingredients are the 2-body S matrix and the dispersion relation referring to 1 and 2 magnon states, and then everything else is given for you by integrability. So now let me finally say that In the more traditional approach, which you would call the algebraic beta ansatz, which is in many ways, for this system much more rigorous and satisfactory, you can obtain these equations directly by operator algebra. It follows from a set of manipulations with the higher conserved charges, similar to solving the harmonic oscillator using raising and lowering operators, that kind of thing. And you can actually derive by purely algebraic methods exactly the same set of equations. So that's the end of the first part of the talk. That's an introduction to what the problem of diagonalizing the dilatation operator looks like at one loop only, and only for this subsection or sector of operators, which I've talked about. So now we want to go on to describe the progress that's been made in attacking the full problem. So first of all, as I said, it's been checked now from both the string side and from the gauge theory side that integrability persists to higher orders. So that motivates the idea that we should assume that integrability is a property of the system, a property of the exact system, until proven otherwise. This is, of course, I'm talking about planar n equals 4 Yang-Mills, not the finite n case. Assume integrability holds for all lambda, and then see what that does for it. Try and derive the general constraints that come from integrability and other things like symmetries, and see if we can constrain the exact spectrum and S matrix. And I should say that this is the approach initiated in a paper by Matthias Staudacher that's been pursued by him and Beisert and other collaborators over a couple of years that's really turned out to be extremely powerful and fruitful, and has led, their program has led directly to this final situation in which the problem is essentially solved, or so we believe. So the approach is to assume integrability for all values of lambda, then to evaluate the constraints of integrability and symmetries of the system on both the exact spectrum and the S matrix. And as I said, those are the ingredients for the beta ansatz equations. However, one thing that's true beyond order by order in the loop expansion, you have to worry about longer range interactions between the magnons. And if you know the S matrix and the spectrum, in fact, that only tells you the asymptotic beta ansatz equations for a very large system. So in this approach, we're not going to be able to learn anything directly about finite length operators, only about very long operators. So having derived the constraints and solved them, and hopefully having arrived at some exact results for the S matrix and the spectrum, you are then, of course, free to go away and expand them order by order in lambda at weak coupling and also at strong coupling, and to compare with explicit calculations on both sides of the correspondence. So this is a program that's been enormously fruitful and has essentially come to fruition in the last year.
Can you remind us what the loop expansion is an expansion in?
The loop expansion in gauge theory is an expansion in the Toft coupling. So the Toft coupling is G squared Yang-Mills times the rank of the gauge group. The planar limit is the limit n goes to infinity with lambda fixed. So an expansion in perturbation theory and Yang-Mills theory, in Yang-Mills or super Yang-Mills, is an expansion in planar Feynman diagrams where each loop will give you an extra factor of the Toft coupling. So let's first talk about the constraints of the spectrum, on the spectrum. I'll review a very pretty analysis that Beisert himself lectured about last week here, so hopefully some of you were at those lectures and this will all be quite familiar. But perhaps I want to say it in a slightly different way to how Beisert described it. So once again, we're going to deal with a very, very long chain, essentially an infinite chain, and we're going to think about operators that we get by introducing various impurities into the ferromagnetic ground state. So as before, the ferromagnetic ground state is the operator with an infinite chain, well, a very large chain of scalar fields x, and eventually we want to put a trace at the end of this chain. But for now, I'm just thinking about a very, very long chain of x's as effectively a spin chain. So the first important thing is that you want to realize how the symmetries of the problem act in this context. The full superconformal symmetry of the n equals 4 theory is a very large supergroup, and it's partially broken by the ground state of the spin chain. This ground state, as I've already mentioned, is an operator from the chiral ring, which has a BPS property. It preserves a fraction of the supersymmetry. And in fact, to be more precise, of the full superconformal group, the ground state, the ferromagnetic ground state, preserves a supergroup which consists of two products of SU2/2. So these are supermatrices that obey, where the generators obey a certain Hermitian and obey a certain supertrace condition. The bosonic part of this group, I should say, is SO4 cross SO4. You get one SO4 from each of these factors. So that's the symmetry which is preserved by the ground state. The ground state of the spin chain is a BPS operator, and this is what's left over after you've considered the symmetries which are broken by the ground state. So it's a very natural idea now that as we have a set of particles in the system, we have these magnon states with a conserved momentum corresponding to different impurities that we can insert here. It's a very obvious idea, very familiar from the study of all sorts of quantum systems, is that if you have a symmetry which is unbroken in the ground state, then you expect your particles to form multiplets of the symmetry. So you expect, in other words, the symmetry to be linearly realized on the possible impurities that you could insert here in the chain. So what Bizet did in a very beautiful paper was to analyze precisely how the symmetry is realized on the set of impurities that you can put into the ferromagnetic ground state. And he made a surprising discovery when he considered how the supersymmetry as algebra is realized on the impurities. He discovered that SU2/2 is actually modified by a central extension which had never been noticed before. The commutator of two of the supercharges of the SU2/2 squared anticommute to give you, there are some indices on here obviously, anticommute to give you a central charge, which is something that involves a gauge transformation. The central charge is actually something that involves a commutator, so it vanishes if you take, the central charge actually vanishes if you take the trace. It corresponds to a quantity which is non-zero only if you allow gauge transformations. And if you consider a gauge invariant quantity by taking the trace of this operator, then you will find that the central charge vanishes. So in the language of these single particle states, that's saying that the central charge depends on the momentum of the particle and it vanishes at zero momentum. So basically, he was able to identify in a very beautiful way what the multiplet of impurities which form up the supersymmetrization of this magnon that I described are. So it's heuristically, basically, one can insert you can insert impurities corresponding to the two other scalar fields in the problem. You have further impurities relating to covariant derivatives acting on the ground state field X, and you have impurities related to the fermionic fields of the problem. So in fact, what he discovered was that the full set of sort of single field impurities that you can insert naturally form a representation of this unbroken supersymmetry that I described. But it's not just any representation. The key thing is that it's actually a short or BPS saturated representation. That's possible because the supersymmetry algebra has a central charge. So it's a very familiar phenomenon in supersymmetric quantum field theory and string theory that when you have supersymmetry algebras with a central charge, there are special short representations which are annihilated by some of the supercharges, which have fewer elements than the generic long representations. And typically, what happens if you find a short representation is that it has to obey, its quantum numbers have to obey exact relations in order for the supersymmetry to algebra to close on the small representation. And in fact, just by the closure of the supersymmetry algebra on this set of states, he was able to derive the exact dispersion relation up to possibly an unknown function of lambda here, which we now believe to be just lambda, as a function of the momentum. So this is a beautiful, purely algebraic approach that Bizet takes, which allows him to basically use the BPS property of now this supermagnon. So now we don't just have Y, but we have a whole 16-dimensional multiplet of these states, and basically derive a universal dispersion relation for them that relates their contribution to the anomalous dimension, which I called the energy on the previous transparencies, to the momentum by precisely this square root formula that still has the periodic dependence on momentum that we expect. So having this exact result, one can of course go now away and compare it in two very different limits. One can look at the weak coupling limit, and at the strong coupling limit, and compare the predictions of this dispersion relation with what we know about from gauge theory and from string theory. So in particular, this exact formula, precisely the algebra does not fix the function of the coupling that appears here, I should emphasize that, but it does fix the dependence on the momentum. So if one expands out the square root, one recovers the square root, the sine squared dispersion relation of the Heisenberg spin chain, and with precisely the prefactor, if you fix this to be lambda, it then matches the one-loop analysis of Minahan and Zarembo. And one can also take a different limit, and I think my discussion of this is going to be curtailed as I'm already 1 hour into the talk. So another limit you can obviously take, if you have an exact formula, you're free to take not just the small lambda limit, but the large lambda limit. And in that limit, as I've already discussed, you expect to be able to describe what's going on in terms of semi-classical string theory, because the sigma model describing the string is weakly coupled. So it's a very attractive feature that this immediately allows you to make contact with the string side of the correspondence. Now this part I will abbreviate, but it's worth noting that there are actually two different limits in which you can make contact with the string side of the correspondence. So now I note here that I've fallen into a bad habit, which is changing my notation to a notation which Bizet uses. He introduces a coupling G, which is proportional to the square root of the Toff coupling. So G, unfortunately, is a change in notation, but the dictionary is displayed there. So basically for large G, or equivalently large lambda, we can think about free string theory on a very large copy of ADS 5 cross S5, large in units of the string length scale. So in particular, this means that we can take two different limits. There are two different limits we can take for the magnon and then compare with what we know about string theory. One limit is a limit where we take the momentum of the individual excitation to go to 0 rapidly as the Toff coupling G goes to infinity. And in this limit, we actually find a relativistic description of what's going on the world sheet. It's actually just the limit, which is usually known as the plane wave limit, in which you're expanding around a speeding string, a string that's moving at the speed of light around the equator of S5. And as I think I mentioned earlier in the talk, that's a limit in which we know what the spectrum of the world sheet excitations is. It's essentially the usual spectrum of string theory, but you have massive excitations rather than massless. So the harmonic oscillators have a mass term on the world sheet. So basically, one gets in this limit a relativistic free field theory. And the previous transparency, so I should write this dispersion relation down so you can see that it's reducing to the right thing. So the exact Bizet dispersion relation, when written in terms of this coupling constant G, looks like this. And one can expand it at large G, and if you scale the momentum, you can reach a regime which we call the plane wave regime, where basically the world sheet theory is free and has elementary massive excitations, which are basically the harmonic oscillator excitations of the string. So indeed, this formula has the correct behavior in that limit, if we identify K as 2 times G times P. But more strikingly, there is also a much more direct limit, where we simply take the excitation and we crank up the Toff coupling, holding the momentum of the excitation fixed. And when we do that, the second term under the square root dominates the first. We can forget about the first. And we end up with something whose energy on the string side grows with the square root of the Toff coupling, or 1 power of this coupling constant G, which I've introduced. So in fact, this is precisely the right scaling for something that's a semi-classical object, a classical string theory solution on the world sheet. That's because, effectively, the coupling constant of the world sheet is 1 over G. So it's quite natural that, for a fixed classical solution, that its energy, because of the overall factor of G outside of the action, will have an energy that grows linearly with G. So in fact, Hoffman and Maldacena were able to identify this excitation in a very nice way in the dual string theory. It relies on an old trick to take the string sigma model, just the bosonic part, restricted to an S2 subspace, because this is the only thing that's relevant to this particular classical solution, and reduce it, imposing the Virasoro condition. And there's an old trick which reduces it to the Sine-Gordon equation. And then, in fact, the integrability and everything that we've talked about, factorized scattering, just becomes immediate from the classical integrability of the Sine-Gordon theory. The Sine-Gordon theory has soliton solutions, and when you reconstruct what those are in terms of the string world sheet, they turn out to be configurations of the string dubbed giant magnons, which look like this. And when you work out precisely what their dispersion relation is, you indeed find that it agrees with the predictions from the exact dispersion relation of Bizet. This characteristic sinusoidal dependence on the momentum appears in this context. So it's
What ensures that this reduction commutes with integrability?
this reduction. Oh, it's basically, it doesn't commute with integrability if you try and do it quantum mechanically, but it's simply a case of imposing the Virasoro constraint and changing variables in the fields. And you can check that because the Virasoro constraints are first class, well, you can identify what is the right symplectic structure. That's the one thing that might change when you impose constraints is the Poisson structure, but you can identify what the correct Poisson structure is. And that will help when you want to quantize it. But at the moment, it's simply a maneuver at the level of the classical field equations. Okay? So we believe that quantum mechanically, provided you use the right Poisson structure, this will be a way of understanding quantum integrability. But at the classical level, there's actually nothing, basically one can check that the conserved charges are in involution of, basically the same conserved charges which are in involution here. And you end up with exactly the same kind of picture, because kinks undergo factorized scattering classically. The only effect of scattering is a time delay, and multi-soliton solutions can be constructed, and they scatter in exactly the way that I described in the context of the spin chain. Their semi-classical scattering, if you like, is precisely factorizable into a product of two-body collisions between kinks. So that just comes from the classical integrability of the Sine-Gordon equation. So you immediately see a lot of the same structure emerging on the string side of the correspondence.
The sign dependence of the momentum, sort of the hint that there was some discreteness.
That's right.
Here it's just geometrical. It's just
Well, it's because the Virasoro constraint links the world sheet momentum to the angular separation of the string endpoints when you actually look at the equations which define the string motion. So as you increase the momentum, the string endpoints, the azimuthal angle separating them becomes larger, and periodicity in momentum space arises because of that. It's basically one of these giant phenomena, like giant gravitons, that you end up with a kind of UV cutoff because your object is growing in size as you increase its momentum.
There's no sign of discreteness of the
Well, having a cutoff in momentum space, in some sense, is equivalent to discreteness, or so it has a continuous translational invariance that's preserved. So you don't see any discreteness in you don't see directly a breaking of continuous translations into discrete translations. But that's a gauge symmetry anyway in this context, so it's not clear whether that's important or not. But you see the same structure emerging, basically the same dispersion relation, and you can even check that the semi-classical S matrix, well, I haven't got onto the S matrix yet, so I won't say anything about that at this point. So just to conclude the final part of the talk, sorry, not the final part, but unfortunately the penultimate part of the talk, I should say that the same story carries through for these bound states. And we now have a conjecture which says what the exact spectrum for the full theory is for all Toft coupling. Basically, it turns out that these bound states that we identified just in the Heisenberg spin chain lift in a very natural way to the full problem and give you short representations of supersymmetry in higher representations of the supergroup that are still short and still have an exact dispersion relation that's fixed by the algebra. The modified dispersion relation now, the only modification is that instead of having 1 underneath the square root, you have the number of magnon constituents. So I emphasize that these are not just single states, but they're now large multiplets of different excitations which have the same dispersion relation. And one can play the same game, checking the occurrence of these states at weak and at strong coupling. So in particular, this reduces to the analysis of bound states that I was talking about at one loop when you take weak coupling. And when you go to strong coupling, you find instead that you find a similar story. In particular, you can scale this number of constituents so that you keep the full dispersion relation even as you take G to infinity. You can scale Q to infinity simultaneously, so that semi-classically you still find this dispersion relation, and you can look for the corresponding solitonic object on the worldsheet, and you do indeed find it. So this whole story of the spectrum fits between the weak and strong coupling limits. Yes.
What's happening to the spin chain analogy as you go?
Oh, okay. So that's a good question. So if you carry on, sorry.
What exactly is the one loop?
So this picture. Oh, what is the one loop spin chain? So if you calculate order by order in perturbation theory, you discover that the pairwise interaction of the Hamiltonian, of the Heisenberg Hamiltonian, which was relevant at one loop, is replaced at two loops by a next to nearest neighbor interaction, and then at three loops the range becomes larger. Okay, so at each loop you add one more space to your interaction length. Okay, so if you're working on a finite length chain of any finite length, you would expect that eventually you know that the loop order, at some fixed loop order, the interactions are just going to wrap around the chain. So this is an orthogonal approach where you simply decide that you're going to take the infinite limit, the infinite spin limit for the spin chain at line 1. So you consider an infinitely long spin chain, and the idea is that in some sense the range of the interaction will be infinitely large now, but it will be exponentially decaying. That's certainly what you see on the string side. So there isn't, if you like, the interaction extends to infinity, but it's exponentially decaying. So that has yet to be verified in detail how that works, because of course we can't go much further in summing up, finding the explicit Hamiltonian than 2 or 3 loops in some subsectors. So I emphasize that this approach, you don't have to know what the Hamiltonian is in this approach. This approach is based on knowing the S matrix and the spectrum of the theory, right?
There are these long-range spin chains.
There are long-range spin chains, and those are the things that we believe will be relevant here, but actually what we're talking about is some resummation over all loops, right? And probably the picture in which it's easier to understand it is thinking from the sigma model, where there are infinite range interactions, but they're exponentially small at large distance, right? So it's believed that by resumming the planar diagrams and getting the full Hamiltonian, you'll end up with a system that looks like that. But at the level of the Hamiltonian, that's far beyond what people can actually do. So, okay, I've only got a short time, I think. I don't want to. I'm going to very, very briefly tell you about the final part of the story, which is the S matrix. So I'll try and just take another 10 minutes at most. So the nice thing about this, so now there is some understanding of what should actually be the exact spectrum of the model for a long spin chain. It's made up of these bound states. But you can also ask the question about what about the S matrix that determines the scattering of the elementary constituents, the magnons. And here Bizet was also able to make progress just by implementing the symmetries of the problem. So in particular, he implemented supersymmetry, basically the fact that the S matrix has to transform in the tensor product of the short representations of supersymmetry that the magnons which are scattering belong to. And he was able to find very restrictive conditions just from supersymmetry invariance of the S matrix, which essentially determine the matrix structure. This is a 256 by 256 matrix. They determine the matrix structure of it up to a single overall phase, which is known as the dressing factor. So the dressing factor is some unknown function which depends on the momenta of the two particles which are scattering, and on the dimensionless coupling constant G, or square root lambda, the top coupling, which is the parameter which interpolates between gauge theory and string theory pictures. So the remaining problem, after Bizet's work, was to pin down what this overall scalar factor is, and see if one can find an explicit formula for it. And in particular, one has to start thinking about what additional constraints one can impose after one has just imposed the constraints of symmetry. I should say that the constraints of integrability are largely built in by now, because we're just considering the two-body S matrix with the understanding that the multi-particle S matrix is given by factorization in exactly the same way as I showed you in the spin chain. So the remaining problem is to find the two-body S matrix, and that boils down after symmetries to finding a single unknown function, two momenta because the problem is not boost invariant, so you can't eliminate one of the momenta by a boost. So it depends on the two momenta of the incoming particles, and it also depends explicitly on the coupling constant. So the remaining progress which has occurred over the last few months is to actually pin down what this dressing factor, which includes most of the dynamics of the problem, what this actually is. So in S matrix theory, there are generically a kinds of constraints that you impose. In the relativistic problem, there is a constraint known as crossing symmetry, which relates the scattering amplitudes for particles to those of antiparticles. Now it turns out that because there is a relativistic aspect to this dispersion relation, you have a dispersion relation with a square root which has two signs, and in fact there are limits where it becomes relativistic. It's very plausible that a crossing symmetry should apply to such an S matrix as this. So Janik conjectured exactly what the form of this crossing symmetry was, and was able to write down the constraint of the crossing symmetry on this unknown function. It turns out to be a nonlinear functional equation which restricts the form of this function sigma. So this was further solved order by order in the strong coupling or stringing expansion by Baizet and Hernandez and Lopez, who found, in some sense, the sigma model perturbation theory expansion of the unique phase which satisfies crossing. Unfortunately, the series which you end up having to sum is asymptotic only, and it's not even clear if it's Borel summable. So it turns out that there is still, even after you've solved the crossing equation, there is still a huge ambiguity in resolving and finding the final form of the S matrix. So the final ingredient which led to a kind of unique answer is another highly conjectural ingredient, which is called transcendentality, which is something completely orthogonal. It goes back to the gauge theory expansion in loops, looking order by order at the loop expansion, and looking at the pattern of transcendental numbers that appear in the coefficients of the loop amplitudes at each order. Loop amplitudes typically involve things like Riemann zeta functions with integer arguments, and there are functions of pi involved as well. So Lipatov was the first person to notice an amazing property of perturbative amplitudes, that perturbative amplitudes can be organized in terms of what he calls the degree of transcendentality. And in the n equals 4 theory, there is actually a conjecture that this degree of transcendentality should be maximal. So it's a conjecture about precisely which transcendental numbers, like zeta 3, zeta 6, and so on, should appear in the perturbation expansion. So whereas Baizet, Hernandez, and Lopez were able to find large families of solutions to the crossing equation, Baizet, Eden, and Staudecker looked at the weak coupling expansion and were able to pin down just one member of these large families, which obeys this conjecture of maximal transcendentality. Again, something that's taken purely out of the air as something that had been conjectured before for the n equals 4 theory. So the remarkable feature is that these diverse requirements actually lead you to essentially a unique answer, although it's not been proven that these requirements on their own fix the unique answer.
It sounds like black magic.
It is black magic.
What's the physical reason behind it?
Nobody knows,
Why would you even...
because it experimentally verified in ridiculous high loop calculations. Okay, but the content of my talk, which would have been the starting point for the next talk if I was giving another talk, is to demystify this and explain why the majority of the structure in this dressing factor is actually forced by analyticity and by what we already know about the spectrum. So I'll just end up by saying a few words about that. So, and I'm really only getting on to the beginning of what I wanted to say about the S matrix and its analytic structure. So one does end up with a conjecture for the S matrix, which is a horrible mess. I haven't even told you what X and Y are, and I don't think I'm going to now. I'll just say that Baizet, Eden, and Staudecker were able to write down an analytic function. X and Y are some reparametrization of the momenta. But of course, what one wants to understand from this formula is why this is the relevant thing. It's been pulled out of the air. Black magic is involved. And in particular, the black magic crossing is black magic because it's certainly an unproven symmetry. It's vaguely plausible, but that's all. Transcendentality is even more black magic. So one wants to understand the structure of this S-matrix and find a different way of deriving it from physical principles rather than from black magic. So how do we go about that? Well, this is a very, very complicated analytic function. And analytic functions are uniquely specified by their singularities. So if we can understand the singularities of this expression, in fact, if we can work out precisely what those singularities are, their positions and perhaps their residues as well, then we can actually reconstruct this function and we'll have some kind of explanation for it. So I don't have time to demonstrate exactly how that works, but let me just say that you do, when you analyze this expression, find a very characteristic set of singularities. You find that the expression only has two simple poles, and well, I should say more precisely the expression for the SU2 sector S matrix. So if you like, this is the all loops completion of the simple expression for the Heisenberg spin chain that I showed you. And x and y are some complicated functions of the individual momenta. But nevertheless, the simplification is that you find that there are just two simple poles, and there is a very specific infinite sequence of double poles. So our work was about relating these singularities to the known spectrum of the problem, because in analytic S-matrix theory, there is a precise relation between singularities of the S-matrix and various on-shell intermediate states. Now, what I emphasized before is that we know exactly what the on-shell intermediate states are. We know their exact dispersion relations. That's like knowing their exact masses in a relativistic theory. Therefore, we can make exact predictions for what the singularity structure of the S-matrix should be. So, in fact, our paper involved revisiting the ancient work of Landau from the relativistic context, which basically gives you the rules for finding the singularities in an S-matrix in a relativistic theory. It's a long story, but basically it boils down to the familiar fact that, for example, a diagram, a Feynman diagram where you have an on-shell intermediate leg here, will give you a pole in the S-matrix. In Feynman rules, that's simply because the propagator for this state has a pole when it goes on shell. And the key thing is, as I've just emphasized, once you know the exact masses of all the particles in the theory, you know all of the singularities, or you should do. It's not quite as simple as that. And in particular, there's a complicated story about higher order singularities where more than one particle can appear as an intermediate state. Those are called anomalous thresholds. And a remarkable feature of two-dimensional kinematics is that double poles are associated with these higher order processes where two particles precisely appear as intermediate states. So essentially our work was about finding the rules, the appropriate rules for locating these singularities in the magnon S-matrix and using the known facts about the spectrum of the theory to predict exactly where the singularities should be. So basically, the Landau rules are a set of rules that tell you that you have to make certain diagrams where all the legs of the diagram are on shell. You have to conserve momentum and energy at each of the vertices and all of the other charges. So essentially, and then there are some other rules that tell you which singularities are physical and which aren't. So basically what we did was to revisit this story and adapt it in a suitable way to the context of a spin chain and a scattering theory where the particles have this strange non-relativistic dispersion relation. We were able to explain, first of all, the simple poles by processes in which the same bound states I described earlier are exchanged in the S channel and in the T channel. And then we were able to go on and explain all of the other poles, the infinite series of double poles, by considering processes in which pairs of bound states, where you allow arbitrary charges for the bound states, appeared as intermediate states in the scattering. So basically what we discovered was that the spectrum of the theory, which is verified by this BPS argument, by the fact that it obeys exact dispersion relations, completely fixes the structure of these singularities in the exact expression of Beisert, Eden, and Staudacher, at least for all of the poles, both the single poles and the double poles. And their expression agrees on the nail in every detail with the predicted poles of the problem, both single poles and double poles. So unfortunately, I didn't have time to explain that part of the story in any detail, but I shall just summarize, as I'm essentially run out of time, that the bottom line, after all the dust has settled, is that for this problem of trying to understand the full spectrum of the n equals 4 theory in the planar limit, for long operators, I explained to you in the first part of the talk that that's essentially equivalent to finding a large set of asymptotic states and the S matrix which describes their scattering. So the problem was to find these, the exact S matrix and the exact asymptotic spectrum. And now there are two conjectures for what those objects are. And those conjectures, first of all, can be tested in huge detail at weak and strong coupling, but they also satisfy an extremely non-trivial cross-check, which is the relationship between the two of them implied by the analyticity of the S matrix. So if these conjectures and their checks survive further verification, that will represent the complete solution of the model in this limit, its complete spectrum and its complete S matrix. The remaining problem is to solve the same problem but in finite volume with the periodic boundary conditions, and that of course is much harder. So I think I should stop there as I'm well over time.
Could you have fixed this dressing function just from your knowledge of the singularities?
No, not really. That would be to make too strong a claim. So the dressing function, in addition from having simple poles, it also has large numbers of branch cuts. So I did say this on one of the transparencies. Not that one. I'll just answer it in words. It also has an infinite set of branch cuts. Now, branch cuts are much harder to pin down. In relativistic theory, they're usually associated with multi-particle thresholds. Okay? And, but usually in integrable relativistic theories, those things are absent because of certain conservation laws. So to really finish the process and really fully explain the analytic structure, we need to understand these branch cuts. Now, I think a lot of the structure of these branch cuts is actually just to do with the branch cuts in the dispersion relations themselves. Basically, the dispersion relations for all the different intermediate states have square root branch cuts in different places that depend on their dispersion relation. So I think in principle, it's a question that you could analyze and hope to pin down, but it's not something that we've succeeded in doing so far.
Any more? Oh well, let's thank Nick again.